Okay, welcome to the June Northwest C++ Users Group meeting. First off, we'd like to thank our sponsors. Thank City of Bellevue for sponsoring our meeting room. We'd also like to thank Cyberdata Corporation for sponsoring our Teams account. We do have a code of conduct. It's basically Bellevue Community or Bellevue City Hall's code of conduct. Pretty straightforward. Be nice to everybody. If you really want to see the full code of conduct, it's printed on the wall by the service desk. Couple of announcements. Yeah. The light rail is now open from Seattle to Bellevue. So if you happen to be in Seattle and would like to attend in person, it's a lot easier to get across the lake now. The Bellevue City Hall is 1 block south of the Bellevue Transit Center. So if you get on the train, it's 1 block to get to this building. We also still have an open speaker slot for October. So if anybody would like to present, just let me know. I do have a couple of ideas if nobody takes that, but we'll put it up for general consumption first. And we have Dan here tonight who has a couple things for CPPCon, if you'd like to.
Oh, just the one. Yeah, the poster program is now accepting submissions. So if you'd like to submit a poster, please do. The information is on the cppcon.org website. There's on the menu, I think the rightmost drop-down menu, you can access the poster program from there. All right, you see the poster program or poster submissions. It's, can't remember what's exactly written, but you can find it.
Okay. Anybody else have an announcement? Start doing that for the general group at some point. Okay. So with that, we'll move on to our feature presentation. Please keep the questions short and focused so everyone gets time to interact with the speaker. And just don't interact or interrupt the speaker when other members are speaking. Okay, with that, I will stop sharing my screen. And yep, you need to start sharing your screen.
All right, yeah, hi everyone, I'm Jatin, and this is a talk about weight-free programming. So I think a lot of you know me, but for those who don't, and I guess even for those who do, this is kind of new. I'm now a student again. I'm doing a Ph.D. at MIT in electrical engineering with kind of a focus on music technology. And when people ask me what I do, lately I've been saying that I'm an audio software developer by day and a signal processing researcher and engineer by night. But really what that means is that I mostly make what I call musical software. And the idea there is it's really anything that would be used by a musician or a recording engineer or someone working in part of the music creation process. And that includes things like, any software that would run on a computer in a recording studio or as part of a live performance, or even like something running inside of a guitar pedal or synthesizer that's like on stage with the musicians. So something that comes up fairly often in the world of audio is this idea of real-time safety. And the way I like to kind of introduce this topic is by thinking about, in software in general, when we do a computation, we want those computations to be correct, which usually means we have some input and we want to map that to some output, and we want that mapping to be correct. In real-time systems, we have a bit of a stricter constraint, which is that we need to generate that correct output within some allowed period of time. And in audio, we often call this kind of allowed period of time the real-time deadline. So if you miss your deadline, then that's essentially as bad as if you'd returned the incorrect result. And one thing that's kind of useful to note about this is that your constraint is really about your worst case performance. So even if you meet the deadline like 99 times out of 100, if you miss that 100th time, then it could still be really bad. And kind of on that note, I guess really what defines a real-time system, like you could say that all software has kind of deadlines that you need to meet in terms of time, but with real-time systems, the constraint is that something really bad happens if you miss the deadline. So for example, maybe you're writing some kind of software that's supposed to help navigate a vehicle autonomously, and if you take too long to kind of generate new instructions for where the vehicle should navigate, then it might kind of get out of sync with the sensor data or whatever you're reading, and maybe your plane crashes or your other vehicle crashes, and so that would be really bad. Or maybe in the high frequency trading world, you have like a very short window of time where a trade would be profitable, and if you miss that window of time, then you could lose a lot of money potentially. I haven't really worked in either of those fields, but I've heard stories. In audio, it's something that's hopefully a little bit lower stakes, but usually you hear kind of a glitch or a pop. And in the kind of technical jargon, we say this is a buffer underrun. And essentially what's happening here is that your computer has these audio buffers that live in your computer's memory, and at kind of a regular interval, those buffers will be sent to your D to A converter and then converted into an electrical signal and sent out to your speakers or headphones or whatever device you're listening on. And you can see here, we've got this buffer that's partway full, but there's a little bit of the buffer here that's not filled yet. And so essentially that's just garbage data. So if that, if the real-time deadline hits and that buffer gets sent out to your speakers, then it could sound, really bad. We don't know what the electrical signal there is going to look like. And so in the worst case, maybe your audio equipment gets damaged or your hearing gets damaged. But even in the not as bad case, it's just going to be an annoying glitch or pop sound, which if you're a musician, you're just not going to use software that is having that kind of problem. It's just going to really annoy you, and you'll choose a different product essentially. So a related concept when people talk about real-time software is these ideas of wait-free and lock-free algorithms. And these are kind of related in that wait-free is sort of a subset of lock-free. So the technical definition for lock-free programming is that some part of your system is guaranteed to be making progress at all times. And so you could imagine maybe one way to achieve this is by just not using locks. So that's sort of true. There's a lot more subtlety to it, which we'll get into later, including kind of this idea of what is a lock even. And I'm also like, this is kind of a negative statement. Like I'm telling you don't use locks, but I'm not telling you what to do. So there's a lot of wiggle room there. In wait-free programming, you have, again, a bit of a stricter constraint, which is that every thread in your system is guaranteed to be making progress at all times. So again, maybe you don't use locks, but there's probably a bit more that we have to concern ourselves with to make our certain parts of our program wait-free. So in audio software, we need our audio thread to be wait-free. The audio thread always needs to be making progress, and technically it needs to be wait-free bounded, but not big on technical definitions, so we won't go too into that. And a lot of the software that I write, you also have a UI thread, and you usually want the UI thread to be wait-free, or at least close to wait-free as well, because maybe you're showing like metering data or animations, or you just have like sliders that the user is dragging around, and you don't want them to like stutter or lag, or you want the user experience to be pretty good. But the audio thread is really where we're concerned about missing deadlines and all these bad things that can happen. So we typically follow a few rules, like we don't hold any locks or mutexes on the audio thread. We don't do memory allocation or deallocation. We don't do any sort of IO or syscalls. And the idea with all of these things is that you don't really know how long they're going to take, at least within some upper bound. So you just don't do them, and we figure out other ways to solve our problems. So I wanted to try to show kind of an example of the sort of problem that I deal with in my regular work. So I'm going to try to play some sounds here, and we'll see if that works. And hopefully the people tuned in online can hear as well. We'll see if it works or not. But the idea here is that this is what's called an envelope generator. So if you're playing like a MIDI keyboard or any kind of digital instrument, you usually have a way to turn a note on and then turn the note off, like by pressing a key down and then releasing the key. And so an envelope generator takes that information and uses it to generate hopefully more interesting modulation signal. So right now we have an envelope generator that's just controlling the volume of our sound. So when I press a key, you'll hear the sound, and when I release the key, sound will go away. And then I'll show you some more kind of interesting things that we can do. Okay. Well, okay. The audio is not working right now. Sorry about that. But yeah, so the idea, you can imagine maybe what it would sound like is that you can, maybe have a slow attack. So this will help the sound kind of fade in more gradually after you press the note on. Maybe you would have like a note with a quick decay. So this would be like a staccato note where you hear it very briefly and then it goes away. Or maybe you would have like a long release time. So the idea here is that you press the note and you release it, and it has kind of a long fade out as it's decaying into silence. And I wish I could show you this example because it sounds a little cooler. But the idea here is that you can use envelope generators to control a bunch of different parts of your sound. Like here, you're sort of controlling the volume again, but here you're controlling like a filter. So this will change the tone of the sound. And that'll kind of evolve over time. I shared the slides with Lloyd, so if you are able to follow the link to the slides later on, you can try these yourself in the browser. And you just press the keys on your keyboard to play different notes. Maybe that's a fun demo for later if people are interested. So the way that this works under the hood is that we're going to represent our envelope data here with these 4 numbers. So the first number is basically how long is the attack time, how long does the sound take to fade in. The second number is like how long is the decay time after the attack is finished. And then we also have a control for like what will be the steady state level of our sound after the decay is finished. And then we have a release time, which just controls how long the tail is after you let go of the note. And this is what we call an ADSR, so attack, decay, sustain, release. And this is like what they call a 4-stage envelope. So that's why you need 4 numbers to represent it. But you can imagine maybe there's a more complicated envelope you would want for your synthesizer or your audio software. Like this is a 6-stage envelope. Or my friend Paul has a synthesizer where they have what's called a multi-segment envelope generator. So the idea there is you can have as many stages as you want, and you can have all kinds of wacky shapes within each stage and make all sorts of funky sounds with that. So in our example struct here, the envelope is just 32 bytes. But you could imagine that if you want a different envelope shape, you would need more bytes. And maybe you have kind of a dynamic situation like with the multi-segment envelope generator, where you don't know at compile time how much data you'll need to represent this envelope. It's also worth thinking a little bit here about the access patterns. So in this case, the UI thread will both read and write our data. So that's basically, it's reading the data so that it can draw the fancy shapes that you're seeing here. And it writes the data whenever you move one of these handles, it'll update the data. But our audio thread is only reading the data. So it's just gonna look at these values and use it to construct this modulation signal and then use that to help make your sounds. So that's kind of the problem that we're trying to solve here. We have this data, we need to interact with it on these 2 threads, and we need the audio thread to be weight-free, and we would like the UI thread to be weight-free. And obviously we don't want to have like data races or other like, bugs or issues in our program. And, presumably we're not allowed to use locks. So how are we gonna solve this problem? So to start, I wanted to kind of go through some, I guess we would call off-the-shelf solutions. So these are things you could just use from the C++ standard library, or things that you could maybe use from like a third-party library or third-party implementation that is usually not too hard to find. So the first thing you could try is just using STD atomic. STD atomic is great in that you can just wrap any object essentially as an atomic, and all of your operations will be, they won't have any data races even if you're working on multiple threads. But the drawback is that you don't know, or you may not know if it's going to be lock-free. So there's this compile time attribute that you can check, which is always lock free. And this will tell you at compile time if you can guarantee that this variable will be lock free in the way that you use it. And typically what decides whether or not your atomic will be lock free is the size of your data. So if your data is less than or equal to 8 bytes, at least in every implementation of the standard library that I've worked with, that means you can get a lock-free atomic for that data. If your data is less than or equal to 16 bytes, then it's a little more of a question. So if both your compiler and the platform that you're targeting support an atomic double width compare and swap instruction, then you can get a lock-free atomic for that data. But it's not something you can reliably, it's not something you can rely on across platforms and across compilers and that kind of thing. So especially if you're like writing code that's going to run on a guitar pedal or something like that, most of those platforms don't support this. And besides, our data was 32 bytes anyway, so none of these things really help us. So what are some ways maybe that we can still solve the problem? The obvious one is just make your data smaller. So maybe you just use a single precision float instead of a double precision float. Or maybe you look at the range and precision that you need for your data and you figure out some other way to encode it such that it can fit into a lock-free atomic. But obviously this gets harder as you have to work with more complicated data structures, like I showed some of the other envelope shapes earlier, where maybe you would need more data to represent what that envelope is doing. So it's actually a little bit hard to find information on this kind of thing. The best place that I've found on CPP reference is the documentation for this function called isLockFree. So if you try to look for information on isAlwaysLockFree, it's not that easy to find. But if you look at the isLockFree function, which is like the function equivalent, although I don't think it's compile time safe. I think only this one's compile time, so you can run at compile time. But anyway, if you look at the documentation for this function, it'll give you some information on when you can rely on your atomic to be lock-free and when, maybe that's something you'll have to check for your platform. So the next solution that I've used a bunch is what I call atomic by parts. And the idea here is that maybe you can't make your full aggregate data atomic, or at least a lock-free atomic, but maybe each individual part of your data could be a lock-free atomic. And that's the case here. An atomic double is usually going to be lock-free. But there's still kind of a question, which is like, is this a valid thing to do? And it depends on what I call tearing. So the idea here is that you have a writer thread and you have a reader thread, and you could imagine a scenario where the writer thread is starting to update the data, and then the reader thread reads some of the data, and it reads kind of a partially updated copy of the data. And sometimes this is okay, sometimes it's not. It really depends on how you want to use the data. There's a lot of instances in the audio world where you can end up with data that's in like an invalid state, or you can have like filter coefficients that lead to an unstable filter, or that kind of thing. So you really have to look at how you're using the data and decide if that's something that's allowable in your use case. The other challenge is that if your data has a lot of parts, this can be really inconvenient. So even if it's real-time safe and everything, you could imagine if you have like an array with 100 numbers, both for you as the programmer and for the computer that's running your code, that could be kind of inconvenient to be doing like a ton of load and stores every time you need to read or write this data. So there's some other things to think about too, besides just, is it lock-free or is it wait-free and so on. So the last thing we can try just using STD atomic and nothing else is an atomic pointer. So even though an atomic envelope data is not going to be lock-free, an atomic pointer to an envelope usually will be. At least on all the platforms that I've worked on, a pointer is 8 bytes or fewer, so that's usually fine. So here's kind of a rough example of how we might do this kind of thing. So we're going to have an atomic pointer to an envelope up here, and then we're going to have this set envelope function that's called on the UI thread. In this function, we're going to get, like for example, in the example I showed earlier, maybe you'll get the positions of your handles and figure out what data you need to construct a new envelope. And then you'll do that. You'll construct a new envelope pointer. And now you can do a pointer swap. So you get the old pointer out, and that lets you delete it. And you don't have to worry about memory leaks or any of that kind of thing. So that's all good. And then on the audio thread, we're going to call this use envelope function. So every time the audio thread runs, this is going to get called. And you're just going to read the latest pointer value and use the data that you're pointing to generate your modulation signal. And so then we're done, right? That's the end of the talk. Unfortunately, it's not. So as I mentioned, set envelope is a UI thread function, use envelope is an audio thread function, and so they could be called at the same time. And when that happens, this old envelope pointer and this latest pointer could be pointing to the same data, which means that when you delete the old envelope, then this pointer is pointing to data that has been freed. And when you try to read that data here, it's like a use after free, and maybe your program crashes, or maybe you read some garbage data that probably do. So unfortunately, this is not a correct implementation, but maybe there's a way that we could make it correct. Maybe there's some solutions we could use. And I've seen a few different approaches for this thing, but the general idea behind all of them is that you have some kind of compare and swap loop on the UI thread. So maybe the way you would do it is, instead of doing a load here, you would exchange in a null pointer, and then when you're done using the data, you would exchange the original pointer back in. And then instead of doing an exchange here, you would do like a compare and swap, where you check if the pointer is null. And if it is, then you can do your swap and delete the old pointer. If it's not null, then you can delete the old pointer. And if it is null, you just loop and check again next time. And you just keep doing that over and over until, eventually you succeed and you're able to delete the old pointer. And this works because you have a guarantee that you're not deleting the live pointer while the other thread is still using it. Now, the obvious problem here is that the UI thread will be waiting until the audio thread is no longer using that pointer, which maybe is a problem, or maybe it's not. It depends on how you're using the data. And it depends on, are you at risk of your UI thread getting kind of descheduled or something for not making progress? But generally, it can be a problem if you have like a UI with animations or that kind of thing, because your UI might stutter while you're waiting in that loop for the audio thread to be done with your data. Now, as a quick side note, you may notice on that previous slide that I was using new and delete, raw pointers, and all these things that are gross and ugly, and we hate them because now we have modern C++, and we don't need to use those things. The great thing with modern C++ is we have smart pointers, and smart pointers are great because they hide the deletion from you. And usually that's great, but for the purposes of this talk, I'm trying to show some code and reason about whether or not it might be real-time safe. And so, at least for demonstration purposes, it's kind of nice to see that delete written out explicitly so that you can say, oh, that's happening on the audio thread, so that's not real-time safe. It's a little bit harder to demonstrate when the only thing I can point at is like an end bracket. So I'll leave these new and delete pointers, new and delete keywords in there for now. The other thing is that I'm going to come back to memory management at the very end of this talk and kind of look at it from a different perspective. So for now, just bear with me. You'll see some new and deletes, and we'll just live with them. And is everyone okay with that? So I know we said that we want everything to be lock-free, wait-free, but we've kind of run out of options with STD atomic. So like, what if we just used like a little bit of a lock and kind of see what happens? So this is what that might look like here. So in this case, we're going to have like a UI thread copy of our data and an audio thread copy of our data. And we'll just use an STD mutex that we can use to synchronize these. And so the idea here is that on the UI thread, we'll just do a simple lock and unlock, and we'll write to our data right in between here. That's easy enough. On the audio thread, we're going to do a try lock, which should be real-time safe. And then if the try lock succeeds, then we'll copy our data and do an unlock. And this is where you run into problems because unlock is not real-time safe. Typically, your standard library implementation of unlock will try to get the operating system to wake up another thread. And that's where you run into problems with like not knowing how long that's going to take and it not being real-time safe. But let's imagine, just for the sake of argument, let's imagine we had some magic way of making unlock real-time safe. Would this be a good implementation? Maybe, maybe not. So you have some other constraints to think about. First off, you need your envelope struct to be trivially copyable because you're doing this copy on the audio thread where you have all these operations that maybe aren't safe. And you also want your envelope struct to be cheap to copy because even if the copy operation is real-time safe, if it takes too long, you could still miss your deadline. And so these constraints may not always be true. For example, if you have a dynamically sized envelope, like with the multi-segment envelope generator we saw earlier, maybe you would use like an STD vector or something to represent that data, and copying a vector is not trivial and usually involves memory allocations and so on. Or another thing we have to deal a lot with in audio is like working with audio samples or audio files, which might be 30 seconds or 30 minutes long or whatever, and copying that much data on your audio thread is usually going to take too long and you're going to miss some deadlines and that kind of thing. So even though this could be real-time safe, if we had a real-time safe unlock, there's still some other things to think about depending on your use case. So kind of going back to this magically real-time safe unlock operation, there is a way that we can make that happen depending on how our mutex is implemented. And specifically, there's a type of mutex called a spin mutex that we use sometimes in audio programming. And I've seen it used in other places and called other things, but the general idea is that you have a real-time safe try-lock operation, since all you're doing is doing test and set on an atomic flag. And then unlock is real-time safe as well, because all you're doing is clearing this atomic flag. So those operations will both be real-time safe. And this will work, but it has a similar problem as your compare and swap loop, because when you try to grab the lock on your audio thread, you're going to get stuck in this while loop while you're waiting for the audio thread to give up the lock. And I didn't really include it here because the details kind of differ from platform to platform, but you're usually going to have some kind of gradual back off strategy where you try the loop a few times and then maybe you sleep a few times and then maybe you yield to another thread or something like that, just so you're not hammering this loop over and over. Who knows how long. So the UI thread is going to hang while your audio thread has the lock. And again, that may or may not be acceptable, but it's typically something we want to avoid. Another thing to point out is that the C++ standard library does not currently have a spin mutex. I heard some rumblings that there was talk of it happening in C++ 26. To my knowledge, it didn't happen. So maybe C++ 29, I guess we'll wait and see. There are other third-party libraries that do have spin mutex implementations, but if you're going to use them, I would recommend kind of reading through the implementation and checking that whatever operations you want to use on your real-time thread are actually going to be real-time safe, because you don't know what that implementation was originally designed for, and it may not work well with your use case. So it's useful to kind of read through these things and get a sense of what they're doing. Another kind of I guess more personal opinion point that I wanted to make is that I kind of don't like spin mutexes. I used to use them a lot, and now I almost never use them. I would say that maybe 95 times out of 100, there's a better solution out there. But every once in a while, it is kind of the only thing that can work. And in those cases, you should definitely use it because it is a useful tool. So everything else we've tried so far has trade-offs that maybe we don't like. So let's kind of bring out the heavy-duty machinery that we use in lock-free programming sometimes, the lock-free queue. And there's a few different ways to implement a lock-free queue, but the way I've typically seen it done is using kind of this ring buffer idea. So you'll have a buffer of kind of slots for your data to live in, and then you'll have a write pointer and a read pointer. And so we have, in this very bare bones implementation, we have a push and a pop operation. And in both of them, we're going to either read or write to whatever slot in the buffer these read and write pointers are pointing to. So here we're writing, and here we're reading. And then we're just going to increment these pointers. And in both cases, this is wait free. You're not stuck waiting on anything. You can just kind of push or pop your data. And if if there's nothing to pop, then you'll get this false return, but you don't have to wait for anything. So you can always use these on your your audio thread or on your UI thread, and they're great, right? So there's no drawbacks at all, right? Well, the one obvious drawback that you might see is that the queue could fill up. So we only have so many slots in our buffer, and if we use them all up, then we have to decide what to do. And the easiest thing to do is just start overwriting your old data. Sometimes that's okay, but sometimes you could lose important data if you do that. So, depends on your use case. The other thing you could do is try to grow your queue. So there's a few implementations I've seen where you have kind of this ring buffer structure, and then you have like a linked list with a bunch of them. So maybe you kind of grow your linked list to add another kind of ring buffer section to your list.
Hang on a sec. Somebody was just asking that.
Yeah.
Somebody put up a note that they cannot hear. Can folks online hear us?
Click on mute icon by your head, John.
Yeah, but the room.
The room's picking it up. Just double check here real quick.
Okay, Stuart says.
Stuart can hear you fine. Okay, so to the person who, that's not going to help. Never mind. Hang on. Joy. Okay, go ahead and keep going. I'll get a chat going with this.
Oh, good. Okay, thank you.
I just wanted to make sure somebody could hear us.
Yeah. Actually, I'll take advantage of the break to drink some water.
Okay.
Yeah. So if your queue is maybe going to fill up, you could try to grow the queue using like a linked list or that kind of thing. But typically doing that is going to require some memory allocation, so you shouldn't be doing that on your real-time thread. There's also some other kind of nice benefits to using a lock-free queue. One thing that's nice is that you can be notified every time your data changes. So with all of the solutions we've seen so far, the reader thread can read the latest version of the data, but it doesn't necessarily have any way to know every time the data has been changed. With a lock-free queue, you get that. And at least to my knowledge, I think it's the only way of solving these types of problems where you get that benefit. So if you need that, then this is really the way to go. The other nice thing with lock-free queues is that there's ways to extend them. I was going to say easily, but it's probably not that easy. There's ways to extend them to use cases where you have multiple reader threads or multiple writer threads or both. Typically, the trade-off is that you can't have all of those threads be wait-free. You have to have a wait on some thread. But it is useful if you have those types of problems to solve. So the way we would use the lock-free queue to try to solve our problem is just by instantiating, in this case, we'll do a queue of pointers, and let's say maybe 512 should be enough for our use case. And you might notice off the bat, this is a little more heavy duty, at least in terms of memory usage, than any of the solutions we've seen so far. So if you're on a platform where you have tight constraints on how much memory you have available, this could be a significant drawback, right? I'll get to the problem in a second. But basically what we're going to do is we're going to have an audio thread pointer to some data. And then on the UI thread, whenever we have an update, we're just going to construct a new envelope and push it into the queue. Then the audio thread is going to check if there's a new pointer in the queue. And if so, it'll pop that pointer and update the audio envelope pointer to be that new value. So can anyone spot the problem that we're running into here? A little bit subtle. So basically, we had a pointer here. And well, I guess maybe another way to say it, you'll notice that there is a new call here, but there's no matching delete, right? So whenever we update this pointer, whatever the old pointer that was in that variable before is going to be leaked, right? So maybe here's another way we could do this where we save the old pointer and then delete it, but that's not real-time safe because we're trying to call delete and we're on the audio thread, so we shouldn't do that. So one option is we could use another lock-free queue to take this pointer and move it back to the UI thread or some other thread where we can delete it. Or maybe instead of a queue of pointers, we use a queue of objects, right? So it'd be like lock-free queue of envelope instead of envelope pointer. And that works fine, but again, we're kind of back at the other constraint that we saw before, where your data needs to be cheap and trivial to copy. Otherwise, you'll have problems with that as well. So to recap all the solutions we've seen so far, they all can work, but they all have trade-offs, right? So STD atomic is great, but your data needs to be small. Atomic by parts is a good solution if you're okay with partial updates. Atomic pointers can work. Your audio thread can be weight-free, but your UI thread will not be weight-free. Thin mutex has a similar kind of problem where your audio thread is weight-free, but your UI thread is not. And now we have this extra constraint that your data needs to be cheap and trivial to copy. And then finally, the lock-free queue, we have kind of two ways to do it. Either we do a queue of data where our data needs to be cheaply and trivially copyable, or we do a queue of pointers, and now we need like a second queue to take care of the old pointers so they don't get leaked. And maybe it's kind of a little more heavy duty than we want. It might seem like a little bit of overkill for the problem we're trying to solve here. But it is nice if you need to be notified every time there's an update. And another concern is that you need to be worried about the queue filling up. So like in a lot of the software that I write, you have maybe like an audio effect where there's like a host that manages the audio thread and the UI thread. And so if the host like pauses the audio thread and the UI thread keeps writing and pushing more things into the queue, then the queue is going to fill up and you'll have to figure out some way to manage that. So all these solutions work, all of them have trade-offs, but what if we want to try doing something that doesn't have any trade-offs, where we get all the things we want and none of the drawbacks, and everyone gets to eat cake for dinner. Let's imagine how we might do that. So let's imagine we could come up with a solution to this problem where our audio thread is weight-free, our UI thread is weight-free, and there's no data races, no memory leaks, none of these other logic bugs or that kind of thing that would make our program have issues. And let's say that for our use case, partial updates are not acceptable. We don't want to have partial updates. And we want our solution to be extendable to any sort of data representation for any type of envelope shape, even if it's not like a shape that we can put a cap on the size of the data at compile time or that kind of thing. And let's say that we want to build on top of STD atomic, but we don't want to go lower than that. We don't want to be looking at like assembly language stuff, and we don't want to really go higher than that and like build on top of lock-free queues or any of these higher level things. So we'll just work with STD atomic and see how far we can get. So if we just start with the writer thread problem isn't actually that hard, right? Our UI thread is the writer thread, and so we'll just have a UI thread pointer to some data, and the UI thread will read and write to that pointer. And you know what, let's make it atomic so that if another thread wants to read it, they can do that too. So here's what we'll do, and this should look familiar because it's exactly the same as the atomic pointer implementation that I showed a few slides ago. So we'll have a UI thread pointer, and on the UI thread, we'll make a new pointer, we'll do a pointer swap, and we'll delete the old pointer. So that's all the same as what we had before. But what we're going to do now is do something a little different on our reader thread. So what our reader thread is going to do is, first off, it's going to have its own copy or its own pointer to work with. And the audio thread will read and write to that pointer value, but we're not going to make it atomic because no other thread has to worry about it. And we're going to go through a few steps here. So the first thing we're going to do is check if the UI thread pointer is null. If it's non-null, then we're going to exchange it with null. So the idea here is that every time the audio thread runs, it's going to do this check. And so we're making sure that that check only fires once per update. So when you do this swap here, now UI thread pointer is null. The next time you check the if statement, it'll skip all of this. And then we're going to take the result of that exchange and store it in the audio thread pointer here. And what's nice about this is that unlike with the atomic pointer algorithm that we saw before, we don't really have to worry about what the UI thread is doing. Even if the UI thread writes to this pointer value in between when we do the check and when we do the pointer swap, it doesn't really matter because the only thing that happens is we get a newer version of that pointer, right? And so the only kind of constraint here is that the UI thread can never write null pointer. It always has to write something non-null. And at least for my use cases, that's never really been a problem. And that's great too, because then we have kind of a guarantee that this pointer will never be null and we can dereference it and do whatever we want down here and not have to think too hard about it. But we still have a bug. Just like with the lock-free queue, we have this old pointer that is still around and is right now going to be leaked if you just try to run this code as it is here. So now it's time to talk about zombies. We have this old pointer that we don't need anymore, but we can't delete it because we're on the audio thread and delete is not real-time safe. So some people call this a zombie pointer in the sense that it's no longer alive, but it's still kind of running around in your program and causing problems for you. So the general way to solve this problem is that you want to get the zombie pointer back to your UI thread or maybe to some background thread. It doesn't matter too much as long as it's not the audio thread. And whenever it's there, we can kill the zombie properly and don't have to worry about it. So as we talked about before, you could use a lock-free queue, but maybe we don't want to do that. Maybe it feels like overkill still. Maybe we have a better idea. So something that I picked up from a friend of mine is this idea of a zombie list, or sometimes it's called a zombie queue, but I'll show you this here. The basic idea is that you're going to wrap your data in a node like a node in a linked list. So you just have a pointer to your next thing in the list. And now instead of an audio thread pointer and a UI thread pointer, you'll have node pointers instead of pointers to your direct data. And then we'll have like a head and a tail for our list. So on the audio thread, everything's basically the same. We do our null pointer check, we do our exchange here, and we're going to save our zombie so that we can add it to the zombie list. So now every time this update runs, you're going to put a new pointer onto the zombie list. And now we have to figure out how to deal with that, right? So the zombie list is getting filled up, and or I guess it theoretically could grow forever, but that would be kind of the same as a memory leak. So at some point, we want to take care of that. So where should we do it? You could do it on the UI thread, or maybe if you have like a background thread that you're already like assigning some tasks to that background thread, then you could do it on your background thread. When should we kill the zombies? Well, maybe if you have like a timer, you say, okay, every like 100 milliseconds, go through and check if there's any zombies and kill them there. Or maybe you do it right before you're about to write some new data. So in the example code I've been writing, we don't really have a background thread. We don't really have a timer set up. So I'll just use the UI thread and I'll kill the zombies right before I write new data. And that'll be fine for this kind of example code here. But the last question I want to ask is, should we kill all the zombies? And I'll let you ponder that for a second. We move on too far. But this is basically the idea here. So we're on the UI thread. When the set envelope method gets called, we'll call kill zombies before we, start doing the new stuff to write new data. And so kill zombies is basically just your standard kind of linked list stuff. You'll loop through your list and you'll kill every entry in the list. And then when you're done, everything is null pointer, so the list is empty. And that's great, except that the audio thread wants to append something to the tail here, right? And so if that tail is null, then maybe things get a little funky. So I don't know, I'm not really like I never really took like a data structures class or anything. So maybe there's like a way to properly do this, but my like first grade solution is you just don't kill the tail. So you always leave something in the zombie list for the audio thread to append to. If anyone has a better idea for how to do this, I'm happy to hear that as well. But for my like kind of silly way of doing it, this has worked pretty well. So now it's time to talk about memory management. I promised we'd come back to it, and here we are. So we've taken care of all the memory leaks. We've taken care of all of these, new and delete problems. We've made sure we're not deleting anything or allocating anything on the audio thread. So now it's time to rewrite everything with smart pointers, right? After all, smart pointers automatically manage allocation and deallocation for every individual object, and that's what we want, right? Well, I kind of don't want that. At least I don't want the individual part. Especially if you're running on like an embedded device or something, I kind of like to be able to like allocate all of my memory ahead of time. So I know like at startup time, how much total memory I'm gonna need. And so if I'm having all these individual, allocations and deallocations, then that kind of gets in the way of that. Really what I want is kind of a managed group allocation, specifically because I have like a pretty, not like straightforward, but I guess kind of consistent pattern for like the lifetimes of these objects, right? So when I first wrote this algorithm, I went through and I tried a few different ways of, allocating memory for these objects. And I'm curious if anyone can guess what was the winner for the allocation strategy that I ended up going with. Any guesses?
Venus?
Close. So I'll give you a hint. This picture is supposed to be a pool alligator. So the winner was a pool alligator. And as a little fun fact, as long as you do everything like I showed you on the previous slide, where you kill your zombies before you write new data, you really only need a pool size of 4. Yeah.
Do you use the alligator to kill the zombies?
Ooh, I should. That's good thinking. Yeah. Yeah, so it turns out you only need a pool size of 4, which again is really nice if you're concerned about memory usage and that kind of thing. If you haven't used a memory pool before, it's pretty simple. You just have like a bunch of fixed size chunks that you can pull from. And whenever you need to allocate something, you just grab one of those chunks and use it. And then when you're done, you just give it back to the pool. And there's a few different ways of kind of doing the bookkeeping for like which chunks are in use and which ones aren't. It's generally not too complicated. So that's the full implementation. That's kind of the full algorithm that I've used. I've been able to use this for a handful of different problems, both like things like the envelope generator and for a handful of other things that I've worked on over the last couple of years. And so I wanted to kind of step back and compare this with the more like off-the-shelf solutions that we looked at before. So compared to standard atomic, we have the nice advantage that the algorithm doesn't care about how big your data is or if it's dynamically sized or not. Unlike atomic by parts, we don't have to worry about partial updates. We'll always get a fully updated copy of our data. Unlike with atomic pointers, we don't have to worry about the UI thread waiting for anything. The UI thread can always be making progress. It won't get stuck. Similarly, with spin mutex, there's no UI thread wait. And also, we don't care about if our data is trivial or cheap to copy because all we're doing is passing around pointers. So we're never doing these copies on the audio thread. And then similarly with the lock-free queue, we have a little bit less overhead. Kind of the total memory usage is generally a bit less. You could argue we have a better way of handling zombies. I guess that's a matter of opinion. So it's kind of up to you and probably depends on the use case. We also don't need to worry about the queues filling up. If the host decides to pause the audio thread or pause the UI thread or something like that, I don't really care. I can just keep reading and keep writing, and whenever the other thread gets turned back on, then things will still work and be fine. As I mentioned before, you are not notified about every update. So you're notified when there is an update, but not about every update. So if you really care about that, you should still use the lock-free queue. It is kind of the only solution I've seen for that problem. And I guess kind of one like exercise for the reader is this algorithm extendable to cases where you have multiple reader threads or multiple writer threads? Does anyone have ideas? So it's a little tricky. So for the writer thread, you can have multiple writer threads, and it generally works fine, but you have to make sure that only one thread is the thread that kills the zombies. So now your like pool allocator business gets a little bit messier and whatnot. But it does work without too many changes. The audio thread is a little trickier because you have this null pointer check here. So the way that I've done this for multiple readers, which is like very ugly, is basically make sure that I know at compile time like a max number of reader threads that I'll have, and then align my data so that I know some number of bits at the start of the pointer will be 0. And then instead of a null pointer check, I just check if that bit is 0 or the bit corresponding to this reader thread is 0, and then you can flip the bit. And then like the zombie list gets more complicated too. So it works, but it's like, it's kind of ugly. So I don't think it's necessarily a good solution to that. probably a lock-free queue would be better or something like that. Or I don't know, I'll talk about something else in a minute here. So that's all. That's the full implementation. That's pretty much everything that I wanted to talk about here. There are a few things that I didn't really cover that might matter for you depending on your use case. So I didn't talk about memory ordering, so you might want to think a little bit more about like acquire and release semantics and how those would apply to this sort of algorithm. I didn't really talk about performance, so this algorithm has been more than fast enough for all of the use cases that I've had for it, but you might need to worry about like the cost of cross-core communication and cross-core like cache line contention, specifically depending on how often you're reading and how often you're writing. So that could end up causing some performance bottlenecks for you. And so the main things I'm hoping that folks here will take away from the talk is that lock-free and wait-free programming is hard. There's a lot of like little gotchas and little things that can take an algorithm that you think will work and cause it to fail for just like a really subtle reason that is very much not obvious the first few times you look at it. And so a lot of times it's easier to just take someone else's solution and use that. That's kind of what I've been doing for most of my career. But even still, it's good to understand the low-level details and be able to look at someone else's solution and at least have a rough idea of why it works and how it works. That said, custom solutions can be good. Even though off-the-shelf solutions can solve a lot of problems for you, writing your own solution can often be a little more lightweight and a little more tailored towards your specific use case. And then you have like more control. I'm a little bit of a control freak sometimes, so I like being able to like have control of everything that's happening, every part of the memory allocation and the thread communication and so on. So it is nice if you want that layer of control. I also wanted to share a few references. So this talk kind of started out as a blog post. So if you want to read this in like text form, you can read the blog post. It's linked here in the slides. Similarly, there's a really great blog post by Timur Dumler, who has a bunch of other like CPP-con talks and so on about real-time programming and wait-free programming. But he has a nice blog post about spin mutexes and shows kind of his implementation for doing that. And then recently I saw this great talk. I'm not going to try to pronounce this guy's name because I'm probably going to mess it up. But he has a really great talk for the Jane Street YouTube channel, talking about a lot of the things I mentioned on the previous slide about performance and where like cross-core communication and cache line contention can cause bottlenecks for you. And then he presents this really neat algorithm called left-right, which is nice if you don't care about your writer thread being wait-free, but maybe you have a lot of reader threads and you need them all to be wait-free and you want them all to be really fast. So that's a really cool algorithm as well that can be useful for this kind of problem. So yeah, thanks everyone for listening, and thanks to Lloyd for inviting me to give this talk. And I'm happy to answer any questions or talk about any other things.
So there was one of your earlier slides where you said there's a problem that something might get deleted while the reader thread is trying to read it. I think it was the atomic pointers.
Yeah.
If you were going to do something like that, could you solve that problem by using reference counting?
So in theory, yes. I remember there was some talk of like an atomic shared pointer being added to the standard or the C++ standard library. So I think that could solve your problem. I remember, I think it was Timur who was telling me that there was some specific detail in the way that atomic smart pointer was, or atomic shared pointer was implemented that made it not real-time safe in some way. So I don't remember the exact detail. But even in that case, I think you are still going to have a wait on your writer thread, because you want to make sure that you don't want the last you don't want the last reference count lifetime to end on your audio thread, because then you're deleting on the audio thread still. So there's kind of some funky subtleties there. So basically, what you would want is,
I was thinking you could like transfer it off to a zombie list.
yeah, so something kind of like that could work as well. Yeah, in general, I think reference counting can work, but I haven't used it specifically for this type of problem. So I don't want to say yes because I don't know for sure. Yeah.
So one thing that occurred to me, and I don't know if you got it or not, have you thought about taking, you've always kind of got the zombie killer thread kind of somewhere, right? Associated with other stuff. What about making it just a dedicated zombie killer thread? It's off in the corner and it's low priority. So when the system just doesn't have anything else to do, it goes and kills zombies.
Yeah,
Have you-
that's
does that-
totally valid.
Okay.
Yeah. So I think I've done that once where I just had like a background thread.
Yeah.
That was like, every once in a while I'll run this on the background thread, and that's totally valid. Part of the reason I wanted to show go. Yeah, part of the reason I wanted to show it this way is just because it's easier
Okay.
for slideware just to say, oh, I'm just doing it here.
Yeah.
And then also for the nice little reveal here that you only really need a pool size of 4 as long as you kill your zombies right then and there. If you do kill your zombies on a background thread, then you potentially need more memory because your zombie list could grow a bit more. And it's harder to have guarantees about what size you'll need.
Yeah, how'd you come up with the 4? That was another question I had. Is that,
So really, I came up with it by running it and just putting a
Just
little
to keep
counter in my
going,
code.
okay.
And then I went back and reasoned about it. So I think it's like you have one that's your audio thread, pointer, one that is getting created here, one that is on your zombie list, and then one that you could be waiting to delete here. I think that's the 4.
Okay.
I wrote it down at some point.
it just happens to be where they're used. or where
Exactly,
they're-
yeah,
Okay, so it's,
yeah.
okay.
So I think if you did figure out a way to like do something smarter here and not necessarily need the zombie list tail to always be something non-null, then I think you could get it down to 3. But at least for my use cases, like 3 versus 4 didn't change too much. Yeah.
Okay, so I missed the beginning, which I apologize for. Was there ever a constraint that the UI thread like had to run, updates had to be considered at audio rate? Was that kind of like a given?
Yes and no. So I think like my general philosophy is like I want the UI thread to be fast. If I drop a frame now and then, it's not a big deal. But I generally don't want the UI thread to wait for the audio thread. Partly because it could cause like stuttering and that kind of thing, and partly because like in plugins and that kind of software, if the audio thread is paused, then the UI thread is just stuck, right? So that's kind of the constraint that I care about. Some people who are like in games programming and that kind of thing, like you really don't want to be dropping frames, I guess. So for their use case, that's probably, I mean, it's not quite audio rate maybe, but it's like kind of similar, like, your 60 hertz refresh rate is kind of your deadline where you kind of need to be having your updates finished by.
Yeah, so like the way I've kind of solved this is like I do some VST programming, but it's mostly embedded, and so I have a sample rate for my analog digital converters and the same sample rate for my digital analog converters, and they're usually
Sure.
clocked. And then my UI thread is usually just mapping physical controls to then state updates in like kind of the audio thread.
Yeah.
And as long as like, if you have modulation sources like as control voltage, I do a lot of modulars synthesizer stuff, that can either be decimated and you can sample and hold to a lower rate if you'd like, but some people don't like that. Or you can just take all of the voltages from your ADC and then your DAC, and then like all that conversion is still audio rate.
Yeah,
But then by deferring kind of pot updates or button switches by a good margin, they're still kind of waiting, but you don't, it kind of solves a lot of your headache of forcing all of those updates to happen every sample.
Yeah. I think kind of for my general use case, I think of it as like what updates need to happen per block versus per sample. And so, yeah, I would say like, I can't think of a situation where I've had to do it any other way, but I think usually my situation is like the UI thread, whatever the UI thread state is at the start of the block, that's what state I use for my audio thread stuff. But yeah, that's a really good question. So depending on like, like for example, you could imagine a case where like you have a really long block size, like a 2-second long block. And so you're like moving a slider, but you're not going to hear the update until like 2 seconds later.
Sure.
So yeah, maybe for that kind of thing, there is a situation where you'd want your updates to come a little bit faster. But yeah, I mean, you'd probably still want it like slower than audio rate in some way, just kind of depending on your situation. Yeah. Oh, yeah.
Hey. Any other questions? Oh, look like Robert's.
Yeah,
Go for it.
seems like they've been making digital recorders and, digital guitar pedals for quite a few decades now. And I kind of thought maybe this stuff would be more standard than still messing around trying to find solutions. Um,
Yeah, I mean, that's a good point. So I mean, this kind of thing has been done for a while. And so like all of the solutions and workarounds that I talked about in like the first half of the talk, I guess, are like things that have been around for at least 10 years, probably a lot of them have been around for a lot longer. And so my, new algorithm isn't really like necessarily 100% better. It's just like a slightly different way of doing things that I prefer and has been useful for me for some use cases. But yeah, I mean, depending on what you're doing, there's definitely multiple ways to solve these types of problems, and things like lock-free queues and that kind of thing have been used for this type of problem for a long time and are definitely valid solutions. It's just I like doing things myself for better and usually for worse, but yeah, that's just kind of me.
Was there ever a like case where there was an allocation on one of the audio for threads today? I didn't like fully kind of see everything.
Yeah, there was a case, I think it was a deallocation.
Okay.
Yeah, it was here.
And that's why you have like kind of the zombies, yeah. Like
Exactly, yeah, yeah. So this is a zombie pointer as well, yeah. Yeah, I should have put the zombie slide here. Yeah. All right.
Question. I'm really, I know very little about multi-threaded programming at this level, but when you actually get into the implementation, do you use any of the new features in the standard or the newer ones like JThreads?
Yeah, sometimes. So in a lot of the software that I write, the host system is kind of the system that's providing the threads for me. So in that case, I don't really have to worry about it at all. But yeah, in some software, I'll use like JThreads or like, I don't know, I've done, what do you call it? The thing where you do like STD async and STD future and like the back and forth there. I kind of don't like that though, because it seems to spin up a new thread for every task. So there's a library, I think it's called BS thread pool, that I've used for some things. I can try to find it here. Yeah, this guy's library. So I've used that for a number of things when I have like background tasks and that kind of thing to worry about. Yeah, it seems to get the job done. And then the other kind of new, fancy new thing, and I guess it's a few years old now in the audio world, is Apple's like audio work groups. So the idea there is that you can get one thread per core with like audio thread priority. And so you can sort of distribute your audio workload over a few cores and still have everything be like as high priority as you could want. So that's kind of nice. And there's a few other like host systems that can give you that kind of thing.
Awesome talk. Thank you. Excellent talk.
Thanks. Yeah, it's a fun one. I don't know. I've written that blog I wrote that blog while I was waiting for my. I was getting new tires on my car. So I need to fill some time.
Four. He said,
Yeah, exactly.
Kick the tires.
yeah, right, talk about parallel processing.
So, quick
I
question,
did. I did a lot of real-time programming, but never with music. And then I'd go home at night and play music. And I wish I had gotten involved in music software, but I never did, other than just using it. Would have been interesting to be on the programming side of it.
Yeah, it's a fun niche. There's not like a ton of people in audio programming, but yeah, there's some definitely some overlap with like high frequency trading and some of those other problems. But I think audio programming usually pays a little bit worse than so,
high frequency trading usually pays pretty well
yeah.
from what I've seen.
Yeah, definitely.
Until you lose money.
Yeah.
I have a question. Can anyone hear me?
Yep, we can hear you. Go for it.
Oh, this is Stuart. I had a question in the chat that you didn't really answer. Can you go back a few slides? It's where you were talking about, it was before the queue. I think it was before that. It related to, you talked about if you've run out of buffer space, you can delete old data. Do you remember that slide?
Yeah, that's
Overwrite
Yeah,
old data,
so-
question mark. If you overwrite old data from the writer thread, don't you have to update the read cursor so the reader will read not, what am I trying to say? Do you think that if you have to delete old data, that the writer thread has to write the write cursor and the read cursor?
Yes, that is correct. So the implementation that I'm showing here is like kind of doesn't handle that case where your queue fills up, right? Yeah, I've seen a couple of different ways to handle it, but the kind of what you mentioned is like the general thing that I've seen where what you would do is like when you would do when you do this, you would also increment the read pointer if your write pointer would overlap the read pointer is kind of how you would do that.
But now you've got a problem because you've got the writer thread updating possibly both the write cursor and the read cursor, and the reader thread should only update the read cursor. Now you've got concurrent race condition on access to the read cursor because they can both write it. So don't you need a lock around the read cursor to get an atomic write?
Yeah, there is a way to deal with this that I don't remember off the top of my head, but there's a nice blog post.
VST tell you if your audio thread's running. It has a silence flag, right? So you can just know not to update your rate buffer, right?
Yeah, but in other scenarios you may not have that
Sure.
convenience. Yeah. So there's this nice blog from this guy. He goes by Moody Camel, I guess, where he kind of talks through his implementation. And I'm pretty sure he touches on that, but I don't remember his solution exactly. But yeah, you're right, that is a problem. And I've seen kind of a couple different solutions in different lock-free queue implementations. So it's not like there's like one solution that everyone.
Okay. I mean, just FYI, I gave up trying to solve this, and just if the buffer is full and the writer wants to write it, it just discards the data. I'm reading data in an embedded system off a UART, trying to put it in a ring buffer for the main application. And if the main application is not keeping up, it's simplest to maybe just drop the new data.
Oh,
Because-
I see. Yeah. So instead of
because I was-
overwriting the old data, you just throw out the new data. That's
Yeah.
totally valid. Yeah.
Then it's lock free because you don't have to worry about, because you've only got one thread updating one cursor. So you don't need any lock.
100%. Yeah, that's a really good point. Yeah. Nice. Yeah. Thank you.
Hey, anyone else?
Just say I usually have a ring buffer or block-free queue, however you want to call it, like on the out in the audio thread to get diagnostic data out, and you can
Yeah.
make semi-intelligent decisions, assuming that like you're okay with some compromise. I mean, like I think all of this is more like an architecture question rather than trying to solve it with an algorithm, because you're gonna get locks somewhere. So,
Sure. Yeah, especially for the kind of the diagnostics thing where like you don't know how much data you're gonna end up needing.
Yeah.
Like ahead of time. Yeah, that's a tricky one.
Okay, should I stop the video now or we've got anything else?
No, is that Lloyd? Lloyd, this is Stuart again.
Yep.
I emailed you personally yesterday. I don't know if this forum is appropriate to like advertise a job. Is that appropriate or no?
It's totally appropriate. Yeah, I did not get your email, so.
Oh, okay.
You
Okay.
got a job for folks? Totally. throw it
Yeah,
out
my
there.
name's Stuart McLean. I work at a small engineering company in Seattle. I'm leaving to take up a new job at UW. So I'm looking for people that might fill my role. We need kind of embedded C engineering. We kind of don't use C++. We can, but our processors are small. We're kind of ARM Cortex-M series microcontrollers. It's in the marine sciences industry. So it's kind of, if you like science, it's a cool kind of left field place to work. There's never a dull day. There's loads of work going on. There's loads of projects. I'll type the name of the company if anyone wants to look at the
Yeah. Tell you what,
URL.
Stuart, if you could email me again, and which email did you use? Do you remember?
Yeah, I found your Lloyd at somebody cyber data.
Cyber Data. Yep, that's my company email. Go ahead and email me at that again. I probably wasn't expecting it and probably thought it was just, some recruiter trying to get my attention or something, which is usually what I get. But send it to me again, and now that I know I'm looking for it, I'll grab it and I will put it on the NWCPP announce channel as well. And I'll
Okay.
get it out to more folks.
Don't we have a
Okay.
place on the website for those too?
Yeah, we do, but it's mostly linking back to recruiter sites. So I don't think we've got a dedicated job site. I think we did at one point, but we haven't.
If we find out more of these, we should definitely add one.
Absolutely,
I'll
yeah.
talk to the web guy, see if I can get him to add something.
Okay. Neat.
Yeah, maybe you could like post my email address so anyone who's interested can get back to me.
Yeah, just send me a blurb you want me to forward on to the announce channel and I'll push it over there.
Okay.
And yeah, and for anybody else listening too, pre-COVID, we used to have recruiters come in and they would advertise jobs and so forth. And as many of you know, that paradigm has kind of shifted for multiple reasons. But if anybody has, jobs or job openings, get those in front of the group, because that's one of the functions of this group is to help people find work, right? Help people find work, help people do work, get people, and frankly, with the chaos of the world in the last decade, that's kind of gone away. So if we can bring that back, that'd be great.
Well, I am most certainly not a recruiter. I am an engineer.
Well, let me rephrase this too. If there are recruiters who want to offer positions to, folks here, we're totally open to that too. I just haven't found any lately. So, I mean, that's part of why we used to do pizza before each meeting, and the recruiters would bring the pizza, but that dynamic has shifted considerably, since COVID, both in the people attending the meetings in person, attending the meetings remote, and in the way the recruiters operate. So,
And then people willing to eat pizza.
Actually, that's for some people. That's people don't necessarily want to eat food in a public place in some cases too now. So, although I haven't heard that one lately, but that's at one point was an absolute concern.
Yeah.
Pizza's not enough. You need beer too.
Yeah, there you go. I think it was at the last NWCPP meeting before
Yeah,
everything went to hell.
we did a pizza feed one year too, where we went out and got it was during COVID actually, I think. Correct me if I'm wrong, but went out to City of Redmond and got one of the picnic shelters. Did a little pizza feed out there. That went pretty well.
That was after.
That was after COVID?
Yeah, it was
Okay.
like a year.
Well, after COVID.
Oh, okay.
A couple years after.
Seems like it was a long time ago.
That last meeting we had.
Yes. Okay, anything else? Okay, I'm gonna go ahead and stop the recording. If folks want to hang around and chat a little bit, we got about 10 minutes before they're gonna throw us out of the room. So, and thank you once again for the presentation. It was excellent.
Last meeting was right after the